Before I get started, I do just want to highlight two of my collaborators here. That's not working. How about this one? Matthias Green and Ben Blackledge, who are the bona fide physical oceanographers here. They did a lot of the hard work here, and I wouldn't be able to give this presentation without them, but they are on the other side of the pond, so they were gracious enough to let me give this talk today. I thought I would start at the beginning today and go all the way back to this plot from Stephen Dole's book, Habitable Planets for Man. And despite the non-inclusive title, I do think it's a classic, and I encourage all of you to check this out because it really captures sort of the theme of this meeting, where he really looked at our solar system and tried to think about what kind of planets might be habitable. In this figure, what you're looking at here, it looks kind of like the habitable zone plot, and that's because it's pretty similar to that. What he called the habitable zone, what we call the habitable zone, he called the ecosphere. And when you look at these limits that he derived, it's surprisingly close to the habitable zone from Ravi Kaparapu's paper. And so what's also here is this line right here, this h squared equals 2. What Professor Dole did was he looked at our solar system and said, well, I think wherever I see a tidal bulge that is in excess of the square root of 2 feet, that planet is tidally locked, or that moon is tidally locked. And so that's the origin of the theory of tidally locked exoplanets, is this plot right here. A couple years ago, or 3 years ago now, I guess, I went through and did all the hard work of solving the coupled ordinary differential equations of tidal theory, and I got a pretty similar result to him. So that's great. So he's 2 for 2 there. I really wanted to bring this plot up because there's this other line that he drew on here that doesn't get a lot of attention, h equals 20, so where the tidal bulge equals 20 feet. That's where he asserted, without any proof, that oceans will wash away the continents. So I've never seen any more work done on that point. But nonetheless, given how well he's done before, I think we want to keep that in mind as we go forward. And it also means that for planets like TRAPPIST-1 that are down here, maybe they only need a thin ocean to actually have no land, which is pretty interesting. But hopefully we'll get to that. I'm not going to really talk about this possibility of erosion here today, but I wanted to just bring that point up because it's been sitting in the literature for 55 years. But this really leads to some motivation for this work that we're describing today. We often think about habitable exoplanets as having liquid water oceans, or at least significant amounts of standing water on the surface. And of course, we all know that the easiest to discover will experience strong tidal forces. And so that leads to the natural question then of how will the oceans of these worlds affect planetary evolution and habitability? And I was at this point several years ago studying this, and I went on a crusade to try and find physical oceanographers to help me explore this possibility. It turned out to be a bit of a challenge, but I finally did when I went to the Ocean Sciences meeting a couple years ago. And that's where I met Matthias Green. And we started working on this. I do want to make this philosophical point here, too, that the physical oceanography community is an active community that studies oceans. And I think that we want to engage them as a community as we think about habitable worlds. And, I don't think we want to present to the world that we have discovered a planet with life on it if we haven't talked to them. So we're really trying to form this core group here of people that are going to study this problem, and I'm going to present a couple of our initial results here where we really looked at our solar system as a template or a guide to think about what the exoplanets might be like. And in particular, what we did was we looked at putative ancient Venusian ocean and looked at what those effects might have been like on it, as well as alternative modern Earths. And I'll describe that in a little bit more detail here in a minute. Before I get to the results, I just want to describe the model that we used. I guess you can't see the title here of the slide, but that's okay. The model is something known as the Oregon State Tidal Inversion Code, affectionately known as OTIS. OTIS basically solves an approximation of the Navier-Stokes equation called the shallow water equations, which basically just is where you assume that the width of an ocean basin is much larger than its depth. And this has been used extensively by the Earth science community to study the Earth's oceans. There's a plot of it down here. I'll describe this in a second. But basically what it does is it takes the satellite altimetry data that from a lot of NASA satellites and measures the height of the ocean and from that backs out how much energy must be being dissipated to explain anomalies in the height of the ocean surface. And that's what you're seeing down here, where you see red. That's where the ocean is especially dissipative. So you'll see that there's a lot of it along the continental margins, through straits. But you'll also see that there's some red just out here in the open ocean. And then I also want to just point out that up here in the North Atlantic, you see a lot of red. And this is due to effects such as undersea mountains. You might convince yourself that these red spots here are where the mid-ocean ridges are. And it turns out that a lot of the dissipation in our Earth's ocean comes from a resonance in the North Atlantic basin, where basically the natural wavelength, or natural frequency, of that basin is in resonance with the lunar frequency. And so there's been a lot of hard work by this community to understand the oceans of our Earth, and so we thought we would take this tool and apply it to other bodies and see what we came up with. Excuse me. So what we did is we started with basically modern Venus's topography to look at Venus. And we, of course, so we don't know what ancient Venus's topography and bathymetry might have been like, but we started here just because it is a known topographical features of a planet are available. And so we then created many sea levels. We ended up focusing on these two, where the sea level was the mean radius, and another one where it was an extra 500 meters of water. That corresponds to these kinds of oceans with these depths and maximum depths here. So something similar to the Earth. And then we looked at a wide range of rotation periods, at least sort of initially. And then we looked at sort of different properties of the ocean, how stratified was it, and we made some assumptions such as that there would be no eccentricity, no obliquity. And I want to be clear that this is just a kind of equilibrium model. There's no evolution here. We just sort of made these assumptions and just asked how much energy was being dissipated and what was the torque and things like that at the time. This result was published last year in AppJ. So let's get to some of these results. So a bit of a busy figure here, so let me walk you through it. The top two pictures here are basically just what the surface would look like, looking at the difference between ocean and land. For the two cases, the sort of nominal and a deep case. And then on the bottom left two figures are basically the results for the modern Venus's rotation rate. So that negative means a retrograde rotation period. And the color bars here are unfortunately different scales, so make sure you're paying attention to that. But what we have here in the top rows here is the tidal amplitude, so basically just how high would the tides be in those regions. And then the bottom is the dissipation, the local dissipation. And I guess I forgot to mention that this is for a prograde 8-day rotational period. And so you can see that in this the retrograde long period planet case, that there's sort of just this band of high tides here around the equator, but the tidal amplitude is only about 15 or 10 centimeters. For reference, the Earth's is about 50 centimeters. And then there's some dissipation down here. Note that there is this resonance here that we found in this case. And then on the right, you can see a much more dynamic ocean was in place. And this is sort of the 0th order result of this, is that rotation rate really matters. You really dissipate a lot more energy with faster rotation. And I think that's fairly obvious if you think about it. But anyway, I then want to show you this sort of summary plot where we looked at some tidal properties as a function of rotation period, because that was sort of that's the primary driver of the tidal evolution. So up here we have dissipation in watts. So the Earth's value is up here at about 2.5 terawatts. What we found is that you can actually the dissipation spans something like 4+ orders of magnitude, depending on the rotation rate. And you can see we have also here there's these different kind of cases, whether we had the sort of the shallow or nominal ocean and whether we had internal stratification or not. The results don't change too much whether you make those different assumptions. The tidal torque also spans a big range. The most intense case we found was where the Venus would despin by 72 Earth days in a mega year. That's instantaneous though, so as it spins down, that changes. But nonetheless, you could induce a huge torque on certain cases that we tried. And then this tidal Q, Alfred talked about this earlier, sort of a scaling factor for tidal effects. it spans probably 3 orders of magnitude, up to about a factor of 1,000, or about 200, or about 100 times larger than Earth, and that's an inverse. If you think about tidal evolution and tidal effects, it's inversely proportional to that Q. So when you have a tidal Q of 1,000, that means much weaker tidal effects. So now moving on to what we looked at, sort of alternative Earths is what we called this project, where we basically took the modern Earth's sort of orbital and rotational properties, and the sun and the moon in their current positions, and then we basically varied the continental configurations of the Earth in 120 different times. There's an online calculator that lets you create all your topographic maps if you're interested. That's what we did. And so we basically used Otis to try and calculate how strong the dissipation would be on these models. One thing we did here to simplify the approach was that we used what's known as a bathtub ocean model, which means there's no seafloor topography here, so just a perfectly smooth seafloor, but we wanted to control for the continents and not worry about how much the different seafloor roughnesses might affect the outcome. What that means is that we have a systematic bias here that dissipation rates are underestimated and tidal Qs are overestimated. And we wanted to test here this idea that's been floating around the literature for quite a long time, that the Earth is in an unusually dissipative state right now. And people argue that because if you look at the moon's current recession, it would suggest that the moon would have hit the Earth about 1 billion years ago. So maybe we're in this special time where the Earth is dissipating a lot of energy. So we wanted to check that out. And this is a paper that's under review right now at GRL. But here is some of the results. So just a quick overview of some of the different kinds of surfaces we considered. So here is a version of the Earth with almost no land, some little bit of land, all the way to where there's just mostly a land planet, but with maybe one ocean or something like that. So this is just to give you a rough sense of what's going on here. And these colors correspond again to the tidal amplitude, so the height of the ocean over the mean due to energy dissipation, going up to something like several meters. And again, the Earth's value is something like 50 centimeters. So that's just kind of to give you to orient you a little bit. When we look at some of these results here, so these are for the whole 120 cases. I know it's another busy plot, but I want you to kind of get the trends here. So here is the total global dissipation on the y-axis. And then what we've done here on the x-axis is we've characterized sort of the complexity of the coastline with this parameter here, which is basically the total length of coastlines on the entire planet divided by the square root of the area of oceans. It's sort of a rough measure of how complicated the coasts are. And all these different points here are color-coded based on how much more or less land was on these planets compared to the modern Earth. And so you can sort of kind of get your head around this a little bit. These 2 points here I want to particularly call out. These are the Earth results we had. This is the actual Earth right here with seafloor topography and roughness included. This is where it is if it was just a bathtub Earth model. And you can see that there's this huge swarm of values here. And the Earth, if it had no seafloor, or at least a flat seafloor, it's kind of right in the middle here. So it's sort of an interesting result that suggests that the Earth is not really in an unusually dissipative state right now. And so from this, we get the sense that there is, again, a huge range of possibilities for how much dissipation can occur on an Earth-like planet in the ocean. So I'm running out of time here, so I want to just give you some conclusions. That says conclusions and future directions up there at the top. So I believe that what we did here was the first application of a terrestrial oceanography tool to another planet. In this case, it was Venus. We found that the tidal dissipation could span 4 orders of magnitude. The same with the tidal Qs could be a huge range, and the torques could also be very large. And then we also looked at changing the Earth's properties, looking at a wide range of these continental shapes. Again, we found this huge range of possibilities in terms of how an ocean responds to tides. And so, of course, we want to think about exoplanets here. That's where we ultimately want to go with this. We found that the implications here then are that tidal locking timescales depend very sensitively on how the ocean actually behaves and how it responds to the tides. And of course, we want to know things like the coastline and exobathymetry, but those are hard things to know, but yet that can really affect the time to scale to tidal lock by orders of magnitude. And I think it goes without saying here that there's not just a single tidal locking timescale. We can't just draw a line on the Hadal zone plots and say this is where planets tidally lock. And so in the future, we, of course, need to expand on this, really start to think about that huge parameter space of exoplanets, looking at different bathymetries, also looking at the different frequencies. We've only looked at Earth and Venus's mean motions here, but of course, M-dwarf planets in the Hadal zone are on week-long orbits. We need to look at things like obliquities, the effects of exomoons, and also of interest within would be the orbital evolution of planets that are in multi-planet systems where eccentricities bob up and down due to interactions with other planets. And finally, we want to understand how tidal heating in localized areas could impact the climate. Of course, that's what we want to get to ultimately in the end. So let's sort of think of this as the end of the beginning. I think we have a good sense, or at least we're getting a sense of just how important oceans are in understanding tidal evolution. And so hopefully we're in a good place to start really thinking about how this applies to exoplanets. So with that, I'll stop. Thank you.